ठीक है.
इतना ज़्यादा zoom out, is it fine? या फिर थोड़ा zoom in जा सकता है?
My name is Kenil Ajudiya, and this is a discussion talk session on the cartography of the skies. Does everyone know what is cartography? Yeah, exactly. So the title then suggests that we are going to map the sky in some sense. Right? So here's the problem. Given a sky like this, let's say you go out in the dark, in the night sky, and you see something like this. You don't see the diagrams and all, but let's say you see some stars and things like that. So now you want to figure out how to communicate the location of the stars with others. Sure, you can point out your finger and so that there it is. But is that robust enough? Will you end up pointing at the same direction every time? No, right? And even if you yourself close your eyes and turn around, if someone turns you around and then you get disoriented, you won't be able to point at the same thing again. It's very easy. So then, what we would like is to define a system, coordinate system, in which we can do this thing robustly, like communicate with each other the location of the stars and other celestial objects with precision and accuracy. So that's why what we can do is that make some grids in the sky. First of all, these grids are not arbitrary. So we need to define some references that we'll take to go to make it communicable with others, right? So that everyone will use the same reference, and it will be like unambiguous. So one of the simplest things that you can think of, let's say you are standing here and you see the horizon, and you imagine that the sky is like a dome. That when you look around and you see that it's a dome, right? So why not apply the concept of latitude and longitudes here? Because that is a good enough map for us, right? If we can map the Earth very easily with using such a system, then maybe we can even map the sky, right? So what is the natural way of imposing the latitude and longitude on a hemisphere like this? Let's see, this is the horizon and you have a hemisphere that you can see. What is the natural way? Anyone? Yes. So you will go in the horizontal direction along the horizon, which will give you different longitudes, and you go up in the elevation, which will give you the latitudes. Now that we call as altitude and azimuth in this language. Like altitude is the angle above this horizon, so it is represented by these horizontal lines. You can see by these horizontal lines that are seen going like this. And for convention, we would like to take the north direction as the reference for the longitudes. So in our Earth map, we have the Greenwich Mean Meridian as the reference, right? So here we choose to take north as just a convention, and then go along the east, increasing from 0 to 90, and then south being 180, and west is 270, so on. Okay. So this is called the Walters system of celestial coordinate, basically, or Walters system. Now, can you point out one difficulty that will arise in this system if you were to use this system everywhere on Earth and at all the times. Okay, it will change seasonally. Okay.
People at different points on Earth might be referring to the same object, but they might have different altitude and circumstances for them.
Exactly. Okay. And what else? One more challenge that you will face if you were to use the system at different times. Rotation, right? So, from past observations of about 2000 years or even more, we know that the sky is not static. It changes, right? The location of the star changes in time. So, the location of the coordinate of the stars or any other object will keep changing with time in the system, which is something which we would want to avoid in some circumstances. So, we need to come up with a better situation, right? Okay. Yeah. So if here you can. Okay, so here you can see that on the bottom right corner, you have the time given. Now, if I fast forward this, time changes, then you see that sky is moving, right? So, okay, before we move on, some nomenclature. This north, east, the letters that are written, they are called the cardinal points. They are called the cardinal direction. The point where is right above this point, the point where everything merges, that is called the zenith. That is the point just over there. Okay. Now, so this system, although it has some limitations, it can be used in a telescopes like this. This is a radio telescope, and because it is very heavy, so mechanically it is easier to build such a motors and system which will rotate along the azimuth and along the altitude. So this is how you can have that. Initially it was pointing like this, and then it got far above. Also, more heavier optical telescopes, there also it is used extensively. So this is the problem that one of you described, that the sky is not static, right? So the stars will go into circles, and that creates a lot of problems for keeping track of the coordinate of each and every object. So there is a nice video. So this is the map of the sky, as you saw. what we will do is define the reference as this. So that sky, the sphere that you saw earlier, it is referred to as the celestial sphere. This is the purple color sphere that you are seeing. And then the center, the equatorial plane is the celestial equator, as we call it. So that is the plane which is like projecting the Earth's equator on the celestial sphere. So imagine that Earth is having the latitudes and longitudes over here. The equator will be at the center, right? If you just extend that to the entire sphere, then it will become this purple line, right? And if you draw the longitudes, then it will be this blue line. So now, and this axis that is shown here is the rotation axis of the Earth. So now what will happen? The longitudes will move with time as the Earth rotates. We have defined this system to move around with time at the same rate as the rotations of Earth, right? So the lines which are perpendicular, the blue ones, they will rotate, and that line is the line where the right ascension is constant. The value of right ascension is fixed, and the declination varies. So the declination is like the latitude, because it is changing along this line, and right ascension is like the longitude, because it is changing along this line. Yeah, so this is how we can measure it. Like, so this will go from 0 to 360 degrees, right? Now just convert that 0 to 360 degrees into 24 hours. So how much will be 1 hour? 15 degrees. 360 by 24. So we label it like that. 0 hours, 3 hours, 6 hours, 6 hours will be 90, then 12 hours will be 90 degrees. 18 hours into 7. And then declination, same as the latitudes, 0 to 90 degrees, plus and minus, both directions. And the place where the pole is, the pole of Earth, that point is called the non-celestial pole, because then it is on the celestial sphere. So any point that you want to locate can be located like this. Like at 3 hours you go 45 degrees up, so that coordinates will be like 3 hours and 45 degrees. Okay. And if you zoom in, then it can be like converted into a planar geometry. Same way that Earth's map are made. So from spherical geometry, it can be projected to paper, and then things will get stretched just the way it happens on Earth. Okay. So now this is all well and good. But then how do we keep track of time, right? Let's say the sky is moving and you want to say that when is some source rising and setting. For that, observe one thing. Let's say you are standing here and there is some source over here.
and this is your reference, some reference of right ascension that you have chosen. So conventionally, it is a point where the trajectory of the sun crosses the celestial equator, which I will come to later on. But for right now, just imagine that there is some reference on that purple line that you are seeing. This so on this line, since imagine that we have chosen some reference, which I will come to later. So from there you are measuring the angle of some source, and you are standing here. Now because the earth is rotating, this source will come here after some time. So here the rotation axis of the earth is pointing out of the plane. That's why you have array going like this. So yeah, it will rotate and this source will come over here after some time. Now this angle is the time that it will take for the source to come above, right? So that is defined as the hour. And the right ascension of this point, which is like overhead, is called the local sidereal time. Basically, it is a that is how we can keep track of time relative to the background stars. How do we keep track of time in like our clocks will take the reference of the sun, right? When sun is overhead, that is when we call it welcome. So similarly, analogously, if we want to take the background celestial sphere as the reference, then we can have the point, the right ascension of this point as the local sidereal time. And you will see that there is little bit difference between the solar time and the sidereal time. The time that we measure with the sun is called the solar time. Now that difference arises because of very peculiar movement of the earth around the sun. So this is the sun, let's say, and the earth goes around the sun. So like if it is 12 noon, then the sun will be like overhead for someone who is standing over here. Then after 24 hours, this earth will rotate, and in one day the earth will also come a little bit ahead in revolution, right? So then after 24 hours, this will be pointing somewhere here, but the sun is over here. So it has to move a little bit more. And that angle, how much will it be? This angle, if you want to measure, calculate. 1 degree, right? How will you get that number? Exactly. So 360 by 365. So in 1 day it will be roughly 1 degree. And 1 degree will correspond to 3 hours and 3 minutes and 56 seconds. Yes. So degrees to hour conversion. So that is what gives rise to the difference between solar time and sidereal time. Because imagine the background stars over here, something. Of course, you can't see them during the day, but equivalently you can take the reference of the background stars at night, like these ones. Once it is here, so they will come at the zenith at that time. But that discrepancy of 3-4 minutes roughly will always be there. So this above head, like 4 minutes earlier than the sun coming over. Right? So that is the local sidereal time, which is a little bit different from the local solar time. And the relation is of course very simple. Our angle is just the difference between local sidereal time. So this angle is the local sidereal time. Right section of this point, right? The right section of that point is entire. And the right section of the source is just this. So the difference is the hour. So hence, if the source is somewhere here, like if it is, so this source is rising, right? The horizon will be like this, and the source is coming up, so it is rising. But if a source is over here, which is about to set, then the hour angle will be negative, which will then translate to that before that much time this source was on the meridian. So meridian, okay, I forgot to define this one thing. Meridian is the line which crosses the so this dark green line that goes from north to zenith and all the way to south is the meridian. And when some source crosses that line, that is called the transit. So this source B is transiting, like it is just crossing the meridian. That's all. Okay. So fine. So we have introduced two things. One is the altitude and azimuth system, and the second one is the right ascension and declination, right? And now, how would the sun go? Where would the sun be? Let's say you have the right ascension and declination grade. So for Bengaluru, this point, the rotation axis of the earth is like this. From this point to us, like very above very near to the horizon. How can we determine that? How can we determine the pole stars? Everyone knows what poles are, right? Right, so that is how we can determine the pole star. Now, how can you determine this angle, like how much above the horizon? So, how have we defined this quantity? Let's say this is the earth and this is the equator. So, this is the rotation axis of the earth. Right? And you are standing somewhere here. This is Bengaluru. Latitude 30 degrees. Roughly. Okay. So then, what will be your horizon? It will be like this, right? You are standing like this. Horizon will be 90 degrees from here, right? So then, our pole star will be at this location, like infinity away. So this angle will be outwards. If you are at the equator, where will you? On the horizon. Imagine that you are standing here, so where will you go? At the horizon. But if you are at the North Pole, then this will be on horizon. And where will be the pole? So now going from here to there, it is, and this is the interaction of two mathematical lines, right? That the angle, this and this angle will remain the same. Can draw a little bit cleaner diagram. But this angle will be the latitude of the face. Right? Agree? So now that is, this is 30 degrees. And let's say the sky is moving like this. So where would you expect the sun to go? What I'm trying to ask is that let's say this is the orbit of the Earth. This is the Sun. Okay. Now, so there will be some normal point, right? Of the perpendicular to this plane. This is the top. Now, and we have drawn basically the celestial sphere around the Earth like this, right? And then there is this celestial sphere which is here, and there is some rotation axis of the Earth. This is the rotation axis. Here is the non-celestial pole. So on this, where do you expect? Let's say this is the 90 degrees plane, normal to this plane. So where would you expect the sun's trajectory to be on this celestial sphere? Sorry? Let's say you have the Earth's celestial sphere, which is defined like around the with the rotation axis being aligned with the rotation axis of the Earth. Then here, where will you expect the sun's trajectory to be along, like throughout the year? Where will on whenever you look, where will you find the sun to be? See, because Earth goes around. So with respect to that celestial sphere, the sun will also go up. It will trace out some trajectory. Where do you expect that trajectory to go? As in with respect to some parameter in the celestial sphere. Okay, let's watch this video and maybe then we will be able to visualize it. So this is the celestial sphere grid that is right. This is the pink one is the plane of the solar system or the orbit of the Earth. See, sun will always remain in that plane, right? The pink one. It will never go off the plane. then what is this angle? The angle between this pink line and the equator.
Hmm.
23.5 degrees. Why?
It's a limit of power.
Exactly. Because this state of the plane of the solar system is straight. So, what are the implications of this? First of all, you will always find the sun to be on that line, right? So, so this software will be basically nothing but simulating the sky at all the time. Using this here, the yellow line that you see is the trajectory of the sun. The pink line that you saw earlier, that is here represented as a yellow line. This one. So this is our north celestial pole, where the rotation axis of the Earth is pointing, and the dark blue line which is emerging from the east, that is the equator, celestial equator. Like equator is projected on the celestial sphere, right? So here is this, and perpendicular to that 90 degrees, we have the celestial equator. And now 23.5 degree is the celestial, is the ecliptic. Ecliptic is the terminology for the trajectory of the sun on the sky. And so here what I have done is I have just transformed the coordinate in such a way that this stars remain constant. The stars are not moving. Time is going, right? You see the time is changing. So you see that the stars are static, but the objects which are in the solar system are moving. For example, this is the moon. This one. And the sun is also here. This is Venus. Sun. We see that in the celestial sphere, the sun is tracing out, the trajectory of it is like this line. And all the other planets and moons of the solar system are all lying in very close to this plane, not exactly in the plane. See, moon is also going here and there. And if you zoom in, these planets are also not like they are not exactly on the plane of the solar system. They are little bit off, but roughly they are on the same plane. And this angle comes precisely because of the take of the rotation axis of the planet with respect to the ecliptic or the plane of the solar system. Now remember that this grid, blue color grid that you are seeing, is something that we have defined on our system, right? And that is what we are taking as the reference. So, naturally, nature has already given us one what would it be? Let's say we want to study something in the solar system. Let's say we want to look at the positions of this solar system objects. It can be some asteroids also, something in the asteroid belt, or it can be other moons of Jupiter, or let's say you want to study the motion of other planets. Then now the planets and all, they are also moving, right? In this coordinate system. For studying the stars and all, it's fine. This coordinate system, the blue one that we have defined, Astrae, their positions are fixed, so we don't have to worry about changing position. Right? Although they also change, but very, very little. Okay, before we go there, one more thing that I would like to mention here is that you see that these two are intersecting over here. This one is the blue line, horizontal line, is the equator, celestial equator, and the yellow, they are both meeting, crossing each other here, and then if I go around, we will meet one more in the opposite direction, right? So those are called the equinoxes. That is when the day and the night are of equal length. Because the sun will then rise exactly from the north and exactly from the east. Sun will then rise exactly from the east and set exactly from the east. And sometimes somewhere here it will be the separation between these two will be maximum, right? That is called the solstice. So in the summer month it will be the summer solstice, in the winter it will be the winter solstice on the other side. Same analog is point. Okay. So can you think of one more coordinate system that you can build over? Let's say if you want to study the motion of the planets. Sorry? Right, good. With respect to the star, we can define it. Or here, see, while defining the motion with respect to the star, there is no problem in that. But it will be motion along two directions, right? It will be moving along the declination as well as along the right side. Let's say you want to study, because we know that they are all moving almost in one direction, almost. Then try to keep track of two. And what another method that we can use? Can you think of one more coordinate grid? It's right there. You can take the plane of the solar system as the reference, analog to the equator, or analog to the horizon, and then take the point which is perpendicular to this as the reference for the length, 90-degree length. And then what would be a natural choice for the zero of the longitude? You are seeing the system. So that is what one system that we can do. Right. coordinate system, where the center is the sun, and it is defined along the equator of the sun. Equator of the solar system. Okay. So now let's go back to the this here. We saw that there is this seasonal changes, right? As the sun goes around the ecliptic, the seasons will change. So when will it be summer, for example? Let's say you want to quantify when it will be summer and winter. Okay, so at this time of the year, we are seeing that the sun is here. Okay, so which time? Let's say currently the sun is over here. Okay. So the blue line, which is here, upper one, is the equator. There is the equator, celestial equator, and there is the ecliptic. So and the sun you can see like it's here. So and also the directions are marked. So this is the west and this is towards the north, this is towards the south. So the sun is a little bit south. So which season will it be in? Will be winter. And similarly when the sun goes around this ecliptic and when it comes on the other side, it will be summer. Right? Now this point where the ecliptic and the equator are crossing the equinox, it has been observed that this point changes with time. So what could be the reason? Why would it change? Is it possible that the entire solar system is changing?
I mean, it's a backdrop of the stars and
Okay, first let's establish that how much would be the motion of the stars? Do you know the distance of the nearest star? Apart from the sun. It is about 4 light years, roughly. And that is the distance that light travels 4 years to reach us from there. And now what is the velocity of, so that distance is a huge distance. And what is the distance of the sun? Sun is roughly 8 light minutes. Right? Because light from the sun takes about 8 minutes to reach you. So then, with respect to the distance between Earth and the sun, the distance to the stars is much larger, right? So how much, let's say if the star is moving with a velocity of 300 or 200 kilometers per you are basically an observer here, and there is a point over at 4 light years. This point is moving with the velocity of 400 kilometers per second. So you want to measure that how this angle will change, right? So what will be the rate of this angle change? This velocity divided by 4 light years. So how much will this number come out? Almost close to 0. Right? So that's why we assume that the stars are small. Over a period of year or even decades, few decades, over many centuries, like millennia, it can vary a little. It will be like 20 years. But for all practical purposes on time scales of a year, stars are static to be fine. Good. And even over millennia, the change is still very small. It's not like you will see that moving by 10 degrees. It is not big. So then what could be the reason why this point, equinox, change? Precession also. Okay. So that is what the Earth is rotating like this, and the orange line rotation axis, it goes around. The blue one is the celestial sphere. This is what happens. Imagine that the rest of the solar system is constant. It's not very easily visible. This is the equator, celestial equator, and then the solar system might get a little bit, maybe 3.5 degree over here. Then if this axis rotates, then if we imagine that the celestial sphere also has to move with it. Oh sorry, this is not the equator, this is the ecliptic. This is the plane of the solar system. And the equator will be like perpendicular to the rotation axis. So this is the plane of the solar system, and this is the heliocentric coordinate ecliptic. Then with the rotation axis, the perpendicular, which is the equator, will also move like this. So the point where it will cut will also change. It will go around. Basically, it's like two planes cutting each other, and then if you imagine that one plane is moving like this, then this point will go. So that is why the equinoxes faces. Now, as you might have noticed here, like this is almost like a circle, but when you zoom in, then you see that there are small. This is a deviation from the circle. There is a grid. There must be a grid line over here, right? You can draw a grid line over there, and then with respect to that grid line, how much is that is what will consider. So there are some small calculations like time scales of months or even very small calculations can be time scale of even days. But on the time scale of months and years, there will be this fluctuation. What could that? Why? What would you think is the reason for that. Okay, first of all, before that, why would the rotation axis of the Earth be this? Right now, I mean now or earlier, because this is a regular moon, but the locations of other objects with respect to the Earth is not found. So your answer was correct, but to a different question. The gravitational pull of other objects is what causes this flux, especially the moon and the sun. Because distance to the sun and the moon, location of the moon and distance to the sun, and also the direction keeps changing. So that is what causes this on a very small time scale. Also Jupiter and other planets. That is what causes this very small time scale fluctuation. But this motion is very large compared to this small fluctuation. So this is like 23.5 degrees. The rotation axis with respect to the solar system plane is moving in a circle of 23.5 degrees. And the time period of this motion is about, I think, 26,000 years. The time period of this going in circle is about 26,000 approximately. Then what could have caused this very systematic with respect to the solar system? Because here the plane of the solar system remains constant. So it has to do something with the early days of the formation of the Earth and the solar system. Only when you have a huge collision with the Earth and that sets the Earth in the motion, right from the early days of formation of the solar system, then you can have such a large. Because if you calculate the momentum, angular momentum, then that will come out to be pretty large. This cannot be explained by small. Apart from that, what we have also observed is something like this. So this is a small time scale variation, right? This small. But what we have observed is that this 23.5 degree, that also changes. This 23.5 degree is split over a period of 41,000 years. And even more interestingly, this also. See the centricity of this orbit. It's an ellipse. The orbit is not circular. So this centricity changes with time. Sometimes it is less ellipsoid, and sometimes it is more ellipsoid. It is quantified by the centricity. If you see, take that this image constant and this changes. So, and this is over a much larger 100,000 years. There is of course decision which is going this 26,000. So all these things are mostly, all these effects are mostly explained by the time when the with compartments of large bodies and all. So that can have such. But this has interesting consequences on the climate of it. We have observed that there is a period of 41,000 years. Ice age. Because now the sun, the earth will be more tilted towards the sun. If it is like glass, then that will give prolonged period of less heat on the polar region. So then, if the polar region receives less heat, when it is away, at that time it will be receiving less heat, and when it is towards, then it will receive more heat. So that correlates with the ice ages of the earth. And there are nice techniques to infer when the ice ages occurs. So that you can ask earth scientists. Okay, so Earth's orbital motion also has important consequences for the climate. Then there is one more interesting coordinate system that we can define. It is with respect to the galaxy. So, let me go back to the. Here we have the galaxy. This is the band of Milky Way. And as you can already see, so again the equator, celestial equator, the ecliptic, and the band of Milky Way. All these three are not aligned with each other, right? There are different angles. So when you are studying the motion of the sun in the Milky Way galaxy, if at all there is any motion, or when you are studying the stars in the galaxy, their motion with respect to the Milky Way, then it makes sense to define a coordinate system having the band of the Milky Way as the horizon kind of equator, and the pole of the galaxy as the pole of the coordinate system also. Like this. Here this is the band of the Milky Way, and you choose the equator along the band and define the reference for longitude at the center of the Milky Way, and then the pole will give reference for the latitude. Now, one natural question might arise: how do you convert between these coordinate systems? We have defined some three-pole coordinate system. How do you change? Let's say you want the location of something in a different coordinate system. Let's take the example of this. So this is the celestial equator and ecliptic. Let's say you know the coordinate of the sun. It will be like in the plane. So how do you convert that number into celestial coordinates, arithmetic, or some other star? Let's say you have the arithmetic of a star, but now you want to know the galactic latitude and longitude of the star. For example, here, do you know what these are? These are the no. Andromeda will not be distant compared to the Moon, even if you will have projection factor. Okay, no, that is not the reason. No, but it's not there. These are the Magellanic clouds, the small and the large Magellanic clouds that were discovered by Magellan. They are in the southern hemisphere. So, what happening is, let's say you know the RNA of this, then what would be the, or even here, let's say you know the galactic latitude and longitude of this cloud, what are the RNA of those clouds? So, we can use the simple rules of spherical trigonometry to convert these coordinates. So, like you have heard of the sine rule in linear geometry, right? Sine of A upon A equals to sine B upon B times B upon C. Similarly, in 3D geometry, spherical geometry, we define this inner angle as the small a. So this is the sphere, surface of the sphere, and this we have cut out, and this is the center of the sphere, and these are the radius of the sphere, and we drew a triangle. So these are great circles. Great circles are the circles on the surface of the sphere whose diameter is equal to the diameter of the sphere, and also whose center of the circle is coincides with the center of the sphere. So these three are, let's say, great circles. This things that are called, and they intersect each other at AB and C. The angles that are these 2 points project inside are in small letters A, B, and C. And the capital ones are these outer arc length of the arc, angular size of the arc. So then the sine rule can be stated like analogs internal angle divided by length. It's like the and the cosine formula is then given by this thing, and there is a complicated another formula, sine cosine. Capital ABC are these bold. And then when you apply all those 3 formulas to geometry like this, let's say you have one system and then you have another system which is shifted. Like, go back to this example. This one. This equator and this equator are tilted with respect to each other, right? So that is the tilt that I was showing over here. So this is that tilt. This is one equator and this is second equator. This is one equator and this is the second. So then with that tilted, and then you draw perpendicular to this one is the latitude of that coordinate, and the perpendicular to this one is the latitude of the first second. These are the latitudes, and here is the reference for these. So then you form an intersection triangle of some source here and here, the source is over here. Then you can convert those intersections. This is just to give an idea that this can of course be interconverted by simple trigonometric rules. Not expecting to understand it very much. Yeah. So that is true in our case also, right? Let's say here. coordinates also. So you see that these coordinates are defined with respect to the Earth. Earth is the center, and then you draw a sphere like this and this.
So in the case of the galaxy system, the center of the galaxy is the
No. So the image that I showed you earlier, this image, this is as seen from the Earth. This is a photograph that we have taken. So it is obviously what we saw from Earth. Now, this is the reference. So this is again projected on a paper, but in reality it is. Imagine that it is surrounded. You are surrounding that this and this end are what goes beyond the back side. So that's why the center of the sphere is still us. But on that, the equator of that sphere, the reference at 0 is what we are saying that it's in the direction of the center of gravity. And then these points are also again, we are like these lines, they are also going up above us and then below. So that's why the center is still the same. So that's why these two are analogous situation. Okay. Now, here is one more image. We talked about what we see in the sky, like stars in the Milky Way and the band of the Milky Way, the bodies in the solar system. What about things beyond the Milky Way? There are more galaxies and gases, accumulation of aggregates of gases, and there is voids between the galaxies, the medium between galaxies, intergalactic medium. So what this picture is showing, here each and every dot is a galaxy. And what this axis is the distance from us, where it's written redshift. What happens is, let's say you have a spectral line. You all know spectral lines in atomic and molecular spectra, right? There is some noise and sensitivity. And this is coming at sharp frequency, right? As a function of frequency. So what happens is this spectral line gets shifted to higher frequency, lower frequency. When it is away from us, very away from us, on a cosmological scale, on the scale of universe, the spectral line, if you observe this galaxy and observe some spectral line in that galaxy, then the frequency of that spectral line will be shifted towards the low frequency, longer wavelength. And that is the amount of shift, similar to Doppler shift that you might have heard of. That the ratio of the shift divided by the rest frequency is the redshift. So then that gives a proxy for distance, like because far away galaxies have a larger shift. That is what Hubble observed. Edwin Hubble. He was recording galaxies in the neighborhood and then getting spectra. And he observed this relation that the velocity, because then this redshift, the Doppler, can be related to a quote unquote velocity. That if this galaxy was moving with at much speed, then it will appear that. So he at that time he knew the distances to these nearby galaxies, and the velocities he measured using redshift from the spectra. So then he got a linear relationship for the nearby galaxies. So large scale of like billions of light years. The universe looks like this. Each and every dot is a galaxy. So there are structures like knots and filaments. You can see somewhere there are like filaments. There is a light. And if you look at the three-dimensional view of this, then there are even more interesting things like sheet of galaxies. Like they are all lying in one sheet, two-dimensional sheet. So on the much larger scale, the universe then looks like this. If you look beyond in the third dimension, if you look in the night sky. Because till now we are dealing with only two dimensions. And then this is one of the theoretical understanding of how our universe began. So we think that there was a Big Bang, and then the universe suddenly came into existence out of nowhere, don't know where, how. And then it underwent a phase of exponential expansion. Like in very short time, the size of the universe, physical size, became much larger than a small ball. And then it is increasing now. Even till now, it keeps increasing. That is what we mean by expanding universe. And then there are galaxies in between all over the place. And this is redshift. Now redshift is correlated with time, right? Sorry? And there is a correlation, but why would you expect that correlation? See, I told you that higher redshift means far away. Right? Now far away means light will take more time to reach us. And because we are looking at everything right now, current epoch, so what we are seeing is we are looking past. So if we see something which is higher redshift, it means it came from a larger distance, longer distance, and which implies that the light originated from there at an earlier time. So that's how we reconstructed this whole thing. And the exact nature of this great that I am showing is a theoretical understanding that is accepted as a standard model cosmology. So this comes under the realm of